Hey y'all, we are Memphis Communiversity and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And what we're going to do today is we are going to continue our shape of curves unit. We learned about increasing, decreasing, and concavity in our previous two videos. Today we're going to learn about relative extrema. So that's going to be relative maximum and relative minimum of functions. What we're going to see is that there's going to be two ways to find relative extrema. It's going to be the first derivative test, which we're going to use a ton. But we're also going to introduce the second derivative test, sort of the lesser known brother of the first derivative test. We need to know both of them, even if we're going to be doing the first derivative test a lot more often, because you never know when the second derivative test will just pop up on an assessment. But let's get started. Let's talk about relative extrema. So relative min or max. So first off, before we get to the rules, what I want to talk about is what does it even mean for something to be relative min and relative max? What are we looking for here? Well, the name is really sort of self-explanatory. We're looking for minimum that are relative. So let's draw a random function. So this is going to be my function. Let's just draw it with a nice little curvy curves. Let's draw it like that. So keep in mind that if you look at this picture, notice that there's hills and there's valleys in this picture. Certainly there's the highest hill and the lowest valley, I guess. But we don't care about that. We care about all the hills themselves. Those are the relative maxes. So if I draw this point, draw this point, draw this point, all of these are the relative maxes. So relative max, and relative max. The relative min, the relative minima are all the valleys. So a relative minimum are the reverse. They're all the valleys. Keep in mind that on the AP exam in all calculus, we use two words interchangeably in this context. We're going to use the words local maximum and relative maximum, but just keep in mind that they're the same thing. And both words work. So for example, if you take this little hill right here, notice that while this hill is not taller than other hills, relative to other points in its vicinity, this point right here, or locally, if you look at the other points, notice that it's the highest point. If you sort of zoomed into this picture, this would be a max. For example, this random point along the hill would not be a max, because no matter how much you zoom in, you will never find a neighborhood around this point right here where it's going to be the tallest one, because it's going to keep sloping up. But if you zoomed into, for example, this point right here, even if it's certainly not as deep as these points right here, this point is the minimum if I zoom into my picture about right here. So that's your relative min or max. Basically, even if you're not the tallest mountain, you're still a mountain. Even if you're not the deepest valley, you're still a valley. Keeping in mind that the tallest mountain itself, the absolute max or the absolute min, those are relative max or min respectively. So the absolute max is still a relative max because you're still relatively higher than all the points near you, or locally, you are higher than all the points that are locally near you. Same thing with the min, but reverse. So just keep in mind that while we're not doing absolute max or min, which is actually our next video, we're going to focus on relative max or min. This is really what we're focusing on. We're trying to find these 3 points, or these 3 points right here, the relative max or min. Just like in our increasing, decreasing video and our concavity video though, we are trying to find the relative min or max of f, but we're never going to draw f. So this is the last time in this video where you're actually going to see hills and valleys. Instead, we're not going to draw graphs of f, and we're going to instead draw sine charts of f prime in order to determine these hills and valleys. So just keep in mind that while we don't draw this ever, this is what we're sort of picturing in our head. If we were to draw the graph of f, we would be finding maxes, meaning hills, or valleys, meaning rel mins. So let's talk about the rules now. If you watched our previous two videos, you would know that the rules are very important. For example, the rules where f is increasing when f prime is positive, and f is concave up when f double prime is positive. Relative min and max have two rules, so let's talk about them. So the first rule, which again we're going to use a lot more often, is going to be the first derivative test. And what it says is, let's use English because we might as well. If f prime goes from positive to negative, at a point x is equal to, let's say, a, that means that f prime f of x, sorry, not f prime, but if f prime goes from positive to negative, that means that f of x has a local max or a relative max at that point. F has a local max. Again, we're using the words local and relative interchangeably. F has a local max at x is equal to a. Before I explain this, let me just write the reverse. The reverse is relative min. So instead of f prime going from positive to negative, a local min is when f prime goes from negative to positive. So if f prime goes from negative to positive, goes from negative to positive. I think I don't have the word from here, so I'm just going to squeeze in the word from. Goes from positive to negative, goes from negative to positive. Let me quickly write this. Then it's a local min. So why is this true? This should be fairly self-explanatory if you think about f prime being slope, and that's what a derivative is. So if f prime is positive, that means you're going uphill, your slope is positive. Then if f prime suddenly turns negative, you suddenly start going downhill. So notice if I run uphill, meaning f prime is positive, and then I start running downhill, meaning f prime is negative, what did I just run over? I ran over a hill, which is a local max. Same thing in the reverse. When f prime goes from negative to positive, you're running downhill because f prime is negative, that's a negative slope. Then you're running uphill, so you have a positive slope. So what did you just run? Well, you just ran over a valley. So it's downhill and then uphill, that's going to be a local min. So that's the first derivative test. It's going to be the same steps basically as our increasing question. What we're going to do is we're just going to take one derivative, then we're going to draw the sine chart of f prime. In order to do that, you need to factor the sine chart of f prime as much as possible. But once we do that and we draw that sine chart of f prime, where it goes from negative to positive will be a local min, and where f prime will go from positive to negative, it will be a relative max. Keeping in mind, again, that we're not going to see relative max or min in our sine charts because we're drawing sine charts of f prime to tell us about the graph of f. But before we do that, we're going to practice a bunch of these examples, let's talk about the second derivative test. So the second derivative test is sort of misnamed. In my opinion, it shouldn't be called the second derivative test. It should be called the first/second derivative test. Because what you do is you need both the first derivative and the second derivative. This is what the test says. The test says if you have a point A and f prime of A equals 0 and f double prime of A is negative, what you're going to have is a local max. Then f has a local max at x is equal to a. So this is a little bit weird because negative is going with max, but let me try to explain it to you. So f prime of a is very important. So what f prime of a guarantees is that there's a horizontal tangent line because tangent lines have point and slope where the slope is the derivative. 0 means that the slope is going to be 0, so we have a horizontal line. And then what we're going to have is either this thing or this thing, depending on if the second derivative is positive or negative. If it's negative, like in this case right here, notice that you're going to be concave down. This is a graph of f, which is why f has a local max. So it's a little bit weird because local max goes with negative, but it's only because of the concavity. You want it to be concave down, you want to be eating the floor, so that means that this is going to be a max. Because we want to be eating the floor. We want to be that upside down U facing towards the ground. If it's a local min, the rule would be f double prime is positive, so you're going to be concave up, you want to be eating the sky. So that's what the second derivative test says. So let me write down the rule for second derivative for local min. So it's the reverse. You still need a to be 0 because you still need that horizontal tangent line, f prime of a. Then you need f double prime of a not to be negative, but you need it to be positive, which is slightly misleading in my opinion because positive goes with min in this case, but it's again all about concavity. As a local min at x is equal to a. So before we go for this first derivative test, let me try to explain the process of the second derivative. The one thing you do not want to do is you do not want to find the zeros of the second derivative. That's not how you do the question. What you do is you find the zeros of the first derivative and then plug it into the second derivative. If it's negative, that means there'll be a local max. If it's positive, that means it will be a local min. But you can't just plug in any single number you want into the second derivative, or you should, again, find the zeros of the second derivative. The only numbers that are candidates for local max or min will be the points that make the first derivative 0, because you do need that horizontal tangent line. But that will be at the very end of the video. For now, what we're going to do is we are going to do this first derivative test business, and we are going to try practicing questions with the first derivative. There is an inconclusive case for the second derivative test. So when f prime of a equals 0, that means that it's neither a relative max or min. So you can have sort of candidates for these guys, especially on our sine charts, where if we don't cross through on f prime, or if our second derivative is 0, that just means that it's not a local max or min. But let me erase the board real quick, and then we'll get to some examples. So I'm going to erase this. I'm going to erase, and we'll do some examples. So my first example is we're going to have the function 3x to the fourth plus 4x cubed. And the question is, find the x's that are the local min or max. Keep in mind that this is slightly different than our previous videos, because remember in our previous videos, usually the answers would be intervals because f is increasing, for example, when f prime is positive on an interval. In this case, because we're finding the tip top of the hill or the very bottommost part of the valley, these are going to be x answers, so like x is equal to 1 or x is equal to 2 or something like that. But for the first part of this video, or really for the first maybe 80% of the video, we're going to be doing the first derivative test as much as possible because it is the easier test. We only do the second derivative test if we're forced to. Basically, if we can't draw a sine chart of f prime, or if whoever's making the assessment tells us to use the second derivative test. So in this case, what we're going to do is we are going to just take the derivative and draw a sine chart. So derivative here, not that bad, just the power rule, of course. Taking the 4, dropping it to the front, letting them mingle. So it's going to be 12x. Of course, we subtract 1 from the exponent, it's going to be 3. Likewise, this is going to be 12x as well, the 3 to the front, and now it's going to be x squared. 3 minus 1 is 2. But remember that we want to draw the sine chart of this little sucker right here, but in order to do that, you first need to factor everything as much as possible. So what I'm going to do is I'm going to take out as much as I can. Looks like I can take out a 12x squared, and I'll be left with x plus 1. So this is my simplified form of f prime, my factored form. Now I'm ready to draw a sine chart. So if you didn't watch our video on sine charts, we highly recommend you watch this. But in this case, we are dealing with a positive function, because once we factored as much as possible, this number is positive. Then we're dealing with something odd, because we're dealing with 3 zeros. Keep in mind that x squared contributes 2 zeros, 1, 2, 3. Then we're going to plot them. This 0 goes with negative 1. This 0 goes with 0, x squared. So these are our 2 zeros that contribute 3 zeros in terms of their multiplicity. Positive and odd starts right here, ends at the top. So it's going to start right here, end at the top. That's our end behavior. Then we're going to sort of draw this sine chart. As we approach negative 1, we look at the factor corresponding to negative 1. In this case, it's x plus 1. Notice it's to the 1, so that's odd, so it's going to go straight through. Then, as we approach x squared, it looks like it's even, the power is even. That means it'll bounce at 0. That's great because we end up where we want to end up, positive, starting at negative, going to positive. Remember, we do not care at all about this picture other than that it tells us the signs of the sine chart. So the thing we want to focus on is that it's negative, positive, and positive. Even if this looks like a max, even if this looks like a min, remember that this is a sine chart of f prime, and the signs of the sine chart of f prime tell us about the graph of that. So now we're ready for the show. So in this case, let's look at negative 1 first. Let's try to consider whether this is a relative min or max. Notice that f prime goes from negative to positive at x is equal to negative 1. So again, I like to think about it, I'm running downhill and then uphill. So that must mean that x is equal to negative 1 is a relative minimum. So at x is equal to 1, f has a relative min at x is equal to negative 1 because, that's the worst b I've ever drawn, because f prime goes from negative to positive at that point. just like normal, we do have to justify our our answer with a sentence. We write the question itself, we write the answer, and we write the justification. The justification being the rule. F has a relative min when f prime goes from negative to positive. Notice that f prime did not change signs at 0, so it was positive, and then it remained positive. That means that f has neither a relative min or a relative max at 0. This point right here is still a critical point because f prime equals 0, but because it didn't go from positive to negative or negative to positive, this one is neither. So it looks like we only have one relative min, in this case the relative min being -1. Again, don't focus on the line itself, just focus on the negative and positives. It went from negative and then it became positive, so this is a relative min. And that's it. So we're going to be doing the same sort of thing for the rest of the video, just various questions. We're going to try to draw the sign chart after taking the derivative and factoring it as much as possible. Where it crosses through the axis, those are the points we care about, like -1 and not 0. If it goes negative to positive for f prime, that's a local min. If it goes positive to negative for f prime, that's a local max. So let's keep going. Let's try some more. So I'm going to erase this. I'm going to erase this. So again, the questions are very, very similar. When you see relative extrema, local max, local min, just take a derivative, draw a sign chart, apply the rule. So the next one we're going to do is minus x cubed over 3 plus 9x squared over 2 minus 4 or something. So time for the first derivative. Again, we're doing local max or min. Probably shouldn't erase that. Local max or min being the same thing as relative max or min. First derivative test. F prime positive negative or f prime negative to positive. So let's get started. What we're going to do is we're going to take a derivative. So even if this is a quotient, we recommend not doing the quotient rule here because the quotient rule is awful. Notice that 3 is a constant. I only do the quotient rule when I have x's but in the top and the numerator and the denominator. In this case, 3 is only in the denominator. So what I can do is I can just do the power rule instead. Instead, if you want, you can write it as -1x cubed and just do the power rule. Notice how easy it is. You take the power, drop it to the front, but the 3 and the 1/3 will cancel. So you're going to be left with just -x, and then you reduce the power by 1, it's going to be squared. So again, we're doing the power rule for these sort of derivatives. It's just so much easier to do than the quotient rule, where we'd have to simplify something nasty, and in this case, it's just a one-step derivative. Same thing with this derivative right here. If you want, you can picture this as 9/2 times x squared because 2 doesn't have a x in it. So what we're going to do is the power rule. We take the 2 and the 2 cancel out very nicely. Looks like we're just left with plus 9x. Then the derivative of -4 is of course 0. So it looks like we're done with this derivative. This actually wasn't the derivative I wanted, but we can keep going. We want to factor this as much as possible. That's the name of the game. So what we're going to do is we're going to take out an x, and then it's going to be -x plus 9. But I still don't view this as factored as much as possible. Remember, when I do this, I like it of the form some number, and then x plus or minus something to a power, x plus or minus something to a power, x plus or minus something to a power. So in this case, because we have a -x, I'm going to do one additional step, and I'm going to take out a negative. So it's going to be -x minus 9. So this is the thing I want to draw the sign chart above. This negative is very, very important because when I ask the question positive or negative, I'm going to answer negative because of this negative. So I'm going to draw the sign chart now. It looks like I'm factored as much as possible. Looks like we have 2 zeros here, 0 and 9. We're dealing with something negative. Again, that came from this negative, trying to factor it as much as possible. So we factored it out. So we're dealing with a negative, and then there's only 2 zeros here, 1, 2. So it's a negative even thing. This is actually a negative parabola, of course. So it's going to cross through like this. Again, we don't even if we're doing maxes and mins, we don't care about this max because this is the max of f prime, but we don't care about f prime. We only care about negative, positive, and negative. Because f prime being negative and positive tells us about the graph of f. So if we were to draw the graph of f, at this point and at this point, it would be a relative min or max. At this point, it would be neither of them. But again, we don't draw the graph of f because it's a little bit difficult and we're not artists. So we're ready for the answer. I like to write the question and the justification before I even do it. So f has a local max. We'll leave some space and write x is equal to something. And what we'll do is we'll write the answer because f prime goes from positive to negative there. Then we'll write the question and justification for f local min. So f has a local min at x is equal again to a number because f prime goes from negative to positive at some point. So let's actually determine is 0 the max or 9 the max. So again, just focus on the signs. At 0, it goes from negative, so f prime is negative, you're running downhill. Then f prime is positive, so you're running uphill. So you run from negative to positive, downhill and then uphill. What did you just run over? You ran over a valley. So in this case, the local min is going to be x is equal to 0. For 9, notice that you're positive and negative, so you're running uphill and then downhill. So it looks like our local max is going to be 9. And that's our answer. So again, nothing too crazy. We took the derivative with power rule instead of quotient rule. We simplified the derivative, we factored it as much as possible, drew a nice little sign chart of it, negative to positive, that's the relative min. F prime going from positive to negative, that's the relative max, and that's all you do. So let's do a few more of these. Nothing will change except the function might get a little bit harder to take the derivative, or we might be doing a harder sign chart because it requires a little bit of factoring. But if you know your derivatives like chain rule and product rule, we should be good to go because the questions are always the same. So let's do another one. So we're going to erase this. We'll keep our little sign up. What we're trying to do, local max or min. And we're going to do, let's say, 3 sine of x minus 2. So this is going to be in my next one. And because this is trig, then usually this is fixed on an interval. So we're going to fix this interval from 0 to 2 pi. So again, what we're going to do is we're going to try to find the local max or minimum. So first off, we're going to take a derivative. Looks like our derivative is 3 times cosine of x because the derivative of sine of x is cosine of x. And finally, the derivative of minus 2 is 0. So there's nothing to do here. We can't do even, odd, positive, or negative arguments. When we draw this sign chart, unfortunately, we just have to know what this sign chart looks like. 3 cosine of x from 0 to 2 pi. So let's fix our interval first. 0 to 2 pi. If you don't know, cosine of x starts on the y-axis at the point 0, 1, because cosine of 0 is 1, and it's going to go like this. It looks like this. I don't care about this minimum point, even though it is pi. What I care about are these zeros, because again, I'm not focusing on the minimum of f prime, which is this is a graph of or a sign chart of it. I'm focusing on the max or min of f, which I won't draw. But in this case, it is going to be at pi. Then we're going to plot the zeros. So our first 0 is going to be, I believe, pi over 2, if I remember the unit circle, and 3 pi over 2. So as I write these rules, just try to think for yourself, is pi over 2 a relative max, or is 3 pi over 2 the relative max? Again, if you want, you can of course label this plus minus plus, because that's what we actually care about in this sign chart. So f has a local max. Maybe we'll stop erasing this one because it's going to be the same one every single time. At x is equal to a number because f prime goes from positive to negative. I do like to write the rules a bunch of times so they sort of become ingrained in my head. It's also something you might not memorize because you're just going positive and negative, but I'm not sure about you. Then f has a local min, of course. At x is equal to a number. Haven't even looked at the picture because f prime goes from negative to positive at some point. So what is it going to be? Well, it looks like this first one, you're going positive to negative, meaning f prime, positive slope and negative slope. That must mean that this is a local max. So this is pi over 2. And then, because we're going from negative to positive, this must mean that it's a relative minimum or a local minimum because you're running downhill and then uphill. What did you just run over? You're running over a valley, not a hill. So it looks like this one is going to be 3 pi over 2. And that's it. Again, these questions are very, very repetitive. Take the derivative, factor it as much as possible, sign chart, f prime going from positive to negative is a local max, negative to positive, that's a local min. So let's do a few more of these where the only thing that we're doing differently is that the derivative is getting a little bit harder. So let's erase this. And let's go for something with some fun friends from the past, maybe. So this is going to be e to the x times x plus 3. Maybe we'll do e to the 2x because I keep doing e to the negative x. So we're going to erase this. We're going to be lazy. We're not going to write the rule again. But again, it's the same thing. F has a local maximum, F prime goes from positive to negative. Keep in mind that you should write these answers, full answers, every time you do this. So first off, we're going to take a derivative. Of course, you need to be careful with derivatives. If you need to use the chain rule, or the product rule, or the quotient rule, you have to do that. So in this case, it's going to be product rule. So it's going to be e to the 2x times the derivative of this one, which is times 1. Then it's the derivative of e to the 2x. Keeping in mind, we have to do the chain rule. We cannot forget chain rule. There is a derivative of that inside function. The derivative of 2x isn't just 1, so we need to multiply by it. So the derivative of e to the 2x is e to the 2x times 2 times keep the same. So this was keep the same derivative, keep the same derivative. Then it was derivative, which included the times 2 because of the chain rule, keep the same. Now, some students want to draw the sign chart right now, but again, just wait a little bit, take your time. Always, you can enjoy these problems as you do them. You cannot draw the sign chart until you factor as much as possible. So what I'm going to do is I'm going to take out an e to the 2x because I want it, again, of the form x plus or minus something, x plus or minus something. So in this case, it's e to the 2x. Then it's going to be 1. Keep in mind that when I factor out an e to the 2x, there's still a 1 here, even if it was written like this. And then it looks like I'm going to have 2x, because I'm factoring this in, plus 6. And that's that. Again, just keep simplifying until you have a form where you can draw the sign chart. E to the 2x, I can just do 2x plus 7. I think I'm ready to draw the sign chart now because it's x plus or minus something. We do have to do with this e to the 2x, but remember that because we're drawing sign charts and not graphs, e to the 2x doesn't affect the sign chart of any graph or any sign chart. It doesn't affect the sign chart itself because e to the 2x, no matter what x is always positive. And when you multiply it by a positive quantity, you will retain your sign. So in this case, when we draw this sign chart, I'm going to ignore this e to the 2x, and I'm only going to draw the sign chart of 2x plus 7. But what I would recommend is not get rid of it too early, even if this is how it always works, because some students get confused when you take it out. But in this case, we're going to take it out, so we have this simple sign chart. This sign chart is just a line. It goes through the point -7/2, because you can do a little bit of math here. You set this to be 0, you get -7, x is equal to -7/2. And then there's only 2 types of lines in the world, or maybe there's 3 or 4, but the ones we care about, it's either going to be a negative slope line or a positive slope line. Remember to not base it off this negative right here. It's y is equal to mx plus b. So it looks like the m is equal to 2. So it's going to go through here. Again, I don't really care about this picture because this is a sign chart of f prime. I only care about negative to positive. So now we're ready to answer the question because we drew a sign chart. Notice that we go from negative to positive. So this one must be a local min. So -7/2. Because you're running downhill, because your f prime is negative, then you're running uphill, it's going to be negative to positive, x is equal to -7. Looks like there's going to be no relative max in this case, so this could be none, because we don't have any points where it goes from positive to negative, and that's perfectly valid. You can have local min without having local max, you can have local max without having local min, you can have neither at all. But that's this question. Let's do maybe one more, and then let's switch over to the lesser known brother, sort of the forgotten brother, second derivative test. But one last question before we do that. Let's do one with ln. So let's erase this, erase my sign. So maybe I'll rewrite the rules one more time, even if that takes up a little bit of time through the video. So we're going to do ln, and then in these parentheses, it's going to be something tricky. Let's do x squared minus 3x. And if you plug in 4 here, you'll get this, of course. So it looks like I want to subtract 4. So this is going to be my next question. So again, we're doing local max or min. So first step, of course, is to take the derivative. Let's be careful with the derivative. What's the rule for ln of x? Well, that's just 1 over x, of course. So it's 1 over this big guy right here. But we shouldn't neglect the derivative of the inside function, of course. The derivative of the inside function is required because of the chain rule. We love the chain rule. But the derivative of the inside function is 2x minus 3. You could write it on the outside, but I'm just going to write it above because it's a fraction. And it looks like this is our derivative. Now we have a fraction, and sometimes students are intimidated when they draw sign charts of fractions. But remember that they're the same as when you draw sign charts of regular functions. You just consider the zeros of everything. You do the even and odd, positive or negative argument the same if you just count everything and you consider everything, because again, we're not drawing graphs, we're drawing sine charts. So in this case, just like normal, you have to factor everything as much as possible. So it's gonna be 2x minus 3, it's gonna be x minus 4, I believe, and then x plus 1. So now that we factored everything as much as possible, again, you just include every single zero, even if it's a fraction. So let's plot the zeros first. This is a sine chart of f prime. Looks like it's going to be -1, and then 3 halves is smaller than 4, so it goes 3 halves, and then 4. Then we ask the argument about positive and negative. Well, it looks like we have a positive thing. It would be negative if there was some sort of negative here. Then we can have all the zeros if we have a fraction. 1, 2, 3 zeros, so it's going to be odd. So it's going to start right here, end right here, something like positive slope lines. That's what positive odd functions are. This is a cubic function basically. So positive odd starts right here, end right here. Keeping in mind that all these guys are to the 1, so it's going to go through on every single one because the multiplicity of each of these factors is 1. So in this case, it's going to go through, and then go through. Again, it's going to be negative, positive, negative, and then positive. If I can write a better positive here. So now we're ready for the question. So first off, I'm going to ask a local max. So f has a local max. I think we've done this enough. But remember that it's where from f prime goes from positive to negative. And also remember that in your justifications, you want to write f prime instead of like it or derivative or just positive or negative. You want to show your stuff. You want to tell the world who you are. So just write it. I know exactly what is positive or negative. It's f prime go from positive, f prime to negative. You can write, of course, the words positive and negative in English. But in this case, what is it going to be? It's going to be x is equal to 3 halves. The tricky part about this question is that you might think that -1 and 4 are local minimum. And that might make sense because they do, at each of these points, go from negative to positive. And as we've discussed maybe 1,000 times throughout this video, f prime going from negative to positive means it's a local min. You're running around a valley. So it's going to be negative to positive. But what I would say is actually, this is a trick question. F actually has no local minimum. No local minimum. And why is this the case? This is the case because while we need to use the zeros of the denominator in order to draw the correct sine chart, we need to make sure that it goes from positive and negative at 3 halves. -1 and 4 are not local minimum. They can't even be considered to be local min or maxes, because when you plug in -1 and 4 into the derivative, or when you plug in -1 and 4 into the function itself, you're going to get something that's undefined. You can't divide by 0, and you can't take the ln of 0 itself. So if you plugged in -1, that's what would happen. So even if these look like local min, just be careful. These are not actually local min. You need them to draw the sine chart, because if you have your sine chart wrong, you might think that 3 halves is a local minimum instead, where it's a local max because it goes from positive to negative. But f doesn't have any relative min, even if they look like this, because the function isn't continuous at those 2 points. You can't plug in those functions. They don't exist the function doesn't exist at those 2 points. So while we need them to draw the sine chart, they don't help in their answer. So when you have these fraction questions, again, they're the same thing. You have a fraction, you draw the sine chart in the same way, but just don't consider the zeros of the denominator. Just focus on the zeros of the numerator, and that's that. So we have practiced a lot of first derivative test questions. Again, you're going to use that a lot, mainly with polynomials like the first 2 questions, maybe with the sine or cosine, maybe with some product rule, maybe with some e's, maybe with some ln's or other fractions themselves. But we're going to end this video with the second derivative test. Again, I would focus on the first derivative test. That's always my first instinct when I like to find local max or min on a Saturday noon. But if your educator, whoever's teaching you, if your teacher, I guess, asks you to do the second derivative test, it's nice to know. And you'll see that eventually you're going to be forced to do the second derivative test because you're not going to be able to draw a sine chart of f prime. This sometimes appears in differential equation free response questions and the dreaded Taylor series free response questions towards the end of AB calculus and BC calculus. So let's focus on the second derivative. So we haven't really visited the second derivative test in a while. We introduced it at the very beginning of the video. But remember, the process is plug in the first derivative zeros into the second derivative If it's a negative, it's a max actually, because you're sort of opening up to the sky. If it's a negative, it's a max, you're opening up to the floor actually. And then if it's if f double prime is positive, you're opening up to the sky, so it's a minimum. So it's opposite what you might expect. F double prime being negative deals with a maximum, f double prime being positive deals with a minimum. Keeping in mind, you do never find the zeros of the second derivative. Those are the inflection points. That's not the local maximum. So let's do this question. So we have f of x, and then let's say 3x squared plus, I don't know, 12x. So this is going to be my question. So again, the first thing to do is we find the zero of the first derivative. This actually might not be the best question. Let's change it before we have the chance. Let's do the original question that we had on the board earlier. Let's do 3x to the fourth and 4x cubed. So this is going to be my function. So again, what we're going to do is we're going to try to find the local maximum using the second derivative test. And it really should be called the first derivative test, second derivative test, because again, you plug in the zeros of the first derivative into the second derivative. So in this case, we're going to take the derivative first. So it's going to be 12x to the third with the power rule, of course, plus 12x squared. We already did this at the very first beginning, but it's going to be 12x squared. It's going to be x plus 1. So then we have x is equal to 0. You can write this on the side. And as x is equal to negative 1. So for the first derivative test, what we did is we draw a sine chart. Now we're going for the second derivative test. So what you do is you take the second derivative. So here the second derivative is going to be, looks like it's going to be 36. Again, it's the power rule, so take the 3, drop it to the front. Subtract 1 from the old exponent to form the new exponent, so it should be squared. Then it's going to be plus 24x. And then 2 minus 1 is 1, so if you want, you can write a 1, but I'm not going to do that. One thing I'm definitely not going to do is I'm not going to try to find the zeros of this second derivative. Again, you do not care about the zeros of the second derivative, which is what some of my students end up doing on tests, which is kind of sad because then they miss it. What you want to be focusing on is plugging in these zeros of the first derivative into the second derivative. So let's actually plug in negative 1 because it's a little bit more interesting. So at x is equal to negative 1, notice we don't draw any sine charts because we're just plugging in at one point, which is why the second derivative test is sometimes forced upon you because you only have information about these points. So in this case, at x is equal to negative 1, we're going to plug it into the second derivative. Again, you take your 0, 0 first derivative into the second derivative. So it's going to be 36 negative 1 squared is just, we'll write it out actually. So negative 1 squared is 1. So this should just be 36 minus 24. This is 12. And notice that the second derivative, we don't actually care about this number. We only care about whether it's positive or negative. Because it's positive, that means that this point, x is equal to negative 1. Remember that it's opposite what you might expect. Positive goes with local min. So at x equals negative 1, this is a local min. No need to draw a sine chart, no need to justify because this is the justification. F prime of negative 1 was equal to 0 and f double prime of negative 1 was positive. So let's do x equals 0 because it's a little bit weird. Notice that x equals 0, that means that we're using x equals 0 because it is a 0 of the first derivative. But notice when you plug it into here, you're going to get 0 plus 0. So actually the second derivative is also 0. So this one was neither. And if you remember our answers to the first question, this matches the answers to the first question. We had something that was a local min at negative 1. And the first derivative test, it went from negative to positive. In this case, we plugged in negative 1 and we got a positive number. So it's concave up. So that means it's still a minimum because it's eating the sky. And then at x equals 0, it bounced when we did the first derivative test. So it was neither a local maximum. In this case, the second derivative is also 0. So this is an inflection point actually. And it's not a relative maximum. But again, hopefully you know the steps. The steps aren't too bad in the second derivative test. You just gotta do it a bunch of times because it's not often asked, so you might forget about it. But there's not much to remember other than two main facts. The first one is use the zeros of the first derivative and plug it into the second derivative. So in this case, the zeros were 0 and negative 1. We took the second derivative and we plugged those points in. And also, finally, remember it's opposite what you might expect. The second derivative being positive means it's a local minimum because you're concave up, you're eating the sky, so you're going to be a valley. Then the second derivative being negative, for example, negative would mean you're concave down, you're eating the floor, so it's going to be a max. Practice the second derivative test, practice the first derivative test. Of course, while this concludes this video, if you want more practice, I'll link our Girls Teach Calculus video in the description below, where one of my former students practices several more of these questions. She does questions that I did, but with the numbers changed and different functions like polynomials, trigs, more fractions, ln's, e's, things like that. She also practices the second derivative test towards the end of her video as well. Be sure to check that out if you want more practice with local max or min or relative max or min, because she might explain things better than I do. But until then, thanks again for watching. Hopefully this was useful for you. If it was, please give us a like and subscribe. We certainly appreciate it. We hope to see you next time in our next video, when instead of talking about relative max or min, every single one of the hills and valleys, we're actually going to be talking about the highest mountain and the lowest valley, the absolute max and the absolute min. So be on the lookout for that. It is quite different than everything we've talked about before, because instead of drawing a sign chart, we're going to draw a table. Hopefully we will see you in that next video, and if we do, we'll see each other then. But thanks again for watching in this video. Thanks again.